Okay, so we're going to look at the limit of sine x equals x as x tends towards 0. This is a nice, simple or nice proof that he said we'd have to understand. So maybe it might be something that he wants us to learn a bit better. And it's not too bad. So if we look at this diagram, we've got three different triangles. We've got the large triangle, we've got the small triangle, and a sector. And what we're going to use is the sandwich principle or the squeeze principle. Obviously, that sector has to have an area between the two triangles. And as the angle gets closer and closer to 0, these three things converge to the same thing. So let's have a look at it. In terms of up here, consider the diagram. Let's look at the large triangle. It's all on the unit circle, so this is 1. So what is the area of the large triangle? Half the base, which is 1 times the height. What is the height? Well, the tan of x is opposite over adjacent, which is BA over 1, which is just BA. So now base is 1 and tan of x equals AB over OA. Since OA is 1, the height is just the tan of x. So the area of that large triangle is half tan x. The area of the small triangle, we can use our formula of half AB sine C. And we know that A and B are both 1 because we're in the unit circle. So it just becomes a half of 1 times sine x. So the area of the second triangle there, the area just becomes a half AB sine C, or a half times 1 times sine x. So the area is a half sine x. And our last one is the area of the sector, which is the area of the whole circle, pi r squared, which is nice because r is 1 again. So it's just pi. Now, what fraction of the circle are we interested in? We're not interested in the whole circle. How would we work it out? If we were working in degrees, it would be theta over 360. But if we're working in radians, we could use theta out of 2 pi because that's the whole lot. If you remember radians, 360 degrees was 2 pi. So what we get is theta over 2 pi times pi r squared from up here. But we know that r equals 1. So what we get is that the area is x over 2. So what we've got is that this x over 2 must be between these two things. And you can see that. So now we'll look at our limits a bit down here. So the area of the sector is obviously between the two. So we know that a half sine x is smaller than x over 2, and which is smaller than a half of tan x. So obviously we can multiply everything by 2 and we get sine x is less than or equal to x is less than or equal to tan x. Now tan x, we don't know too much about it, but we know that that's sine x over cos x. Now what happens to cos x as x tends towards 0? Well, cos x, if x is 0, cos of x is 1. So what we end up with is sine x over 1. So we get this thing here, which is sine x is less than or equal to x is less than or equal to sine x as x tends towards 0. So what we end up with is that sine x must equal x. Now, hopefully that explains that little proof that he did. And as I said, it's a nice little app that I've used in the past. I just found that on GeoGebra. It's a nice, simple little app that I've used in class to explain that. And it gives a nice visual of why are they equal. Well, those three things, as it gets closer and closer to 0, obviously, or become equal. Okay? Hope that explained that a little bit. Thanks. Bye.